Hello everyone. Okay, this video I'm going to talk about still talk about harmonic oscillator. Okay, but we are going to using a different perspective to study the simple harmonic oscillator. Before the start, the harmonic SHO. Okay, just interesting stuff is called just called because at the beginning I say all pendulum is also an oscillation, an example oscillation, but we're not going to talk about pendulum in very detail because pendulum is a very complicated system. Okay, it's really complicated. And but what I want to share is the pendulum. Okay, because previously we have the get the obtain the information of what's the period of the harmonic oscillation. Let's see. Okay, we still found because we found the period of a simple harmonic oscillation is related to its mass. Okay, yeah, right now it's not a period, but omega times period equal to 2 pi, right? So if you 2 pi divided by omega, yes, this is a period, and the period is related to the mass of the system. Okay, mass of the simple harmonic oscillator. But the interesting in the physical pendulum, it doesn't. The period is not nothing to do with the mass. Once the rope, once the rope is the same, once the rope length of the rope is the same, no matter what mass it is, the period is still the same. Okay, it doesn't relate to the mass. So there's a very famous example of this, but you can build it on. You can watch this video by yourself. This is a real man experiment to show you the period of a pendulum is nothing to do with the mass of the system. Okay, in this video, it used a small ball, the same length, the pendulum with the same length, but it used a small ball measure the period. And then the teacher, the lecturer, the Walton Newton, I forgot his name. Okay, he used himself as the other example. Okay, its mass is different. It must be different from the small ball. Okay, so he do his experiment by himself and measure the period of the pendulum again, and of course with the same length of the rope. And the experiment really shows the period of pendulum is nothing to do with the mass. Okay, it's very interesting. Okay, but pendulum really used a lot in engineering field. We'll mention something about it later. Okay, let's go back to the harmonic oscillator. And in previously, I say we have two perspective for simple harmonic oscillator. Okay, one is using equation of motion. Yeah, one is using equation of motion. Solve the solution of differential equation. We got the position function. Yep, we got position function and velocity function and acceleration function. This is from, and then we calculate some examples. Okay, this is one way to study the simple harmonic oscillation. It's using equation of motion. Okay, Newton's second law. You're using equation of motion. But actually, because we have learned energy conservation, right? And we have learned the concept of energy. So we will use the tool using we were using energy perspective to study the simple harmonic oscillation again. Okay, but we still have to use the example we have in the from the equation of motion of the simple harmonic oscillator, and previously we get a position function and velocity function, right? And so we have learned energy conservation, or total energy of the system is the kinetic energy plus the potential energy. Okay, kinetic energy very simple, 1/2 times mass times velocity square. And in this system, yeah, we assume it's a horizontal moving, horizontal doing the motion on horizontal surface, so there is no height change, so there is no gravitational potential energy. But this system is a mass spring system. The mass is connected to a spring. Okay, the spring, we have the spring force and we have elastic potential. Okay, elastic potential is 1/2 times the elastic constant or force constant and times the x squared. X is a compression value or stretch value with respect to the equilibrium position. Okay, okay, let's. Okay, and we get our we put our solution of equation of motion in there. So x v is this minus omega a times sine omega t plus phi, and x is a amplitude times the cosine omega t plus phi. Put it over in there. Put it in there, and we will reach a very looks like a kind of complicated solution. Okay, but it's not like complicated at all. Okay, because first of all, we can use a different way to simplify results. Okay, first of all, what can we do? Okay, what can we do? Okay, first of all, we can use, okay, don't forget, in a simple harmonic oscillation, in mass spring system, what's the omega? Omega square is equal to k over m, right? So we can put the omega square k over m into here, okay, omega square into k over m, and then this will become 1 over 2 m and mk a square, okay, and cancel out, so it will become, this will become what? Okay, okay, this will become, sorry, this will become 1 over 2 k a square times sine square omega t plus phi. And the second term is 1 over 2 ka square cosine square omega t plus phi. So we get a little mass here, sine blah 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 plus cosine blah blah blah. Yeah, because the blah 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 is the same, so I don't want to write it out. Okay, so in sine square plus cosine square is equal to 1. So if we replace this, we replace the omega square by k over n, we will reach this conclusion. The total energy of the simple harmonic oscillation is 1 over 2 times force constant times amplitude square. Okay, so amplitude relates to your total energy of the system, or more specifically, amplitude square. Amplitude square. Okay, so that's the first way. First, we have first kind of substitution. But we also can have another substitution. Okay, what about another substitution? Let's see. We can use another substitution. So use the use the same mathematical relationship. Okay, kind of annoying. It's just the same thing, but omega square equal to k over m. So we can replace k by k equal to m omega square. So we can replace k by m omega square, and the second term will become 1 over 2 m omega square, and 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 become a square cosine omega square blah 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 blah. And the first term is 1 over 2 m omega square a square sine square blah 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 blah. Okay, so because we use the same trick, sine, we add these two terms together, cosine square plus sine square equal to 1. So we'll have another result. The total energy is equal to 1 over 2 times m times omega square times a square. Okay, but if you remember the results, the Vmax in a simple harmonic oscillation is equal to omega A. Okay, remember that? So actually, this omega square A square actually is a Vmax square. Okay, so we kind of reach this conclusion. The total energy of the simple harmonic oscillator is 1 over 2 Ka square and also equal to 1 over 2 m and Vmax square. Okay, this kind of very useful relationship, especially for your homework problems. Okay, homework problem, I think you use this relationship a lot. Okay, so this just from energy perspective to this is the energy, very basic energy perspective for the simple harmonic oscillation. We actually we just use the results from the equation of motion. It's okay. So equation of motion is very important. Okay, and then you have put the result as the result of equation of motion into the simple energy analysis of simple harmonic oscillation. Okay, so that's the basic idea of the energy of the simple harmonic oscillation. And the next one, let's look a little deeper, not deeper, and let's discuss the kinetic energy and potential energy of the simple harmonic oscillation in more detailed way. Okay, so we just get our results. Okay, use our the result. I just obtain the kinetic energy is 1/2 k square sine square ka square times sine square. Yeah, just this term. Don't forget because if we replace omega square by k over m, we will obtain the kinetic energy is 1/2 ka square times a sine square function. And the potential energy is 1/2 Ka squared times the cosine square function. Okay. Okay. It's if we draw the picture of the kinetic energy and elastic potential energy as a function of time, just this graph. Yeah, this is the function of time. I think it's a function of time, or I'm not sure the horizontal axis is omega t or t. I'm not sure. But anyway, no matter what, okay. I think omega t is much more reasonable. Yeah, I think it's omega t. I'm not sure. Omega t. Okay, let's see. It's omega t. Okay, omega t. Or no, omega t is also a function of time. Okay, you will see the kinetic energy. Yeah, the total energy is the same. This line is total energy. This line is total energy of the system. And what's the value? Don't forget, it's 1/2 Ka squared. That's the total energy. And you see the kinetic energy is a sine square function. Okay, this is sine square function here, sine square function, sine square function, sine square function over here, sine square function. And also, and the spring potential energy is a cosine square function. Cosine start from 1, right? And sine start from 0. Okay, sine start from 0. Not about 0. Yeah, sine start from 0. And cosine starts from 1, right? And times 1/Ka squared. So it starts from 1/2 Ka squared. So this is a cosine function, cosine square function. Okay. And you see this, the potential energy and the kinetic energy, they are both keep doing oscillating. They're oscillating. They are both oscillating. And the other very interesting thing is when the kinetic energy reach the maximum, your potential energy goes to minimum, right? And if your potential energy reaching the maximum, your kinetic energy reaching the minimum. Okay, so that's why the kinetic energy. This graph tell you the kinetic energy and potential energy. How would I say, the interchange to each other. Okay, it's very interesting. That's why in textbook it give you this graph. Okay, in the textbook it give you this graph. You see the potential energy and the kinetic energy. They exchange. They interchange to each other during a simple harmonic oscillation. First of all, you have full potential energy, and then it transfer and it's oscillating. It becomes and decrease of potential energy, but at the same time, kinetic energy is increased, right? And your kinetic energy decrease at the same time, your potential energy is increased. Okay, this decrease, this increase, so they are interchanged to each other. It's energy conservation. So it's very interesting. Yeah, in the system, your both energy are doing oscillating. Kinetic energy and potential energy are doing oscillation, and they are complementary to each other. One is maximum, the other is minimum. The other is minimum, the other is maximum. Okay, it's very interesting. Okay, and more interesting things that the average energy, the average kinetic energy and average potential energy in the period. Okay, okay. If you from this graph, it's very easy. Where is the average? Where is the average? Where is the average of the kinetic energy? From this, you just observe this graph. What is its energy? what is the average energy of the kinetic energy? No, average kinetic energy in a period. Okay, but very easy. If you look at this graph, this is kinetic energy, right? This is kinetic energy. Based on this graph, what is average? What average you think? I think average is here, right? Okay, and then and this one, let me see. Okay, this is a kinetic energy curve here. So if it's a one period average, I think that's the average kinetic energy in one period. And what's the line? What's the other? This is potential energy, right? This is potential energy. And what is average? Based on this graph, where is the average? I think our average is still here, right? The average potential energy. Okay, so the average kinetic energy and unit and average potential energy in simple harmonic oscillation is also the same. But in fact, it's feel from this observation of this graph, yeah, they're the same. But if we really do the calculation, yeah, just really do the calculation. Okay, I'm not asking you can do this integration because maybe you just learn calculus in this semester. So maybe you are not that familiar with the integration right now. So the integration, you can do this integration. It's just the kinetic energy. This is potential energy, and do the integration in a one period and divide it by period, the time, the period. Okay, the other is then potential energy, do the integration in one period and divide it by period. And the integration actually is not that difficult because this is constant, 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 constant. So after all, you just do the integration of the sine square function. And this is also the same here. This constant, k is constant, a is constant. So you're actually doing the integration of cosine square function. And the integration of sine square function in one period is 1 over 2. And the integration of cosine square function in a period is also 1 over 2. So you get the 1 over 4k squared. The other is also 1 over 4k squared. And that's coincide with the observation that this graph is right at the middle. And I previously said the total height is not total height. The height of this graph is 1 over 2 Ka squared. That's total energy. So in the middle is 1 over 4 Ka squared. Okay, the calculation results and observation of graph is the same. Okay, that's why it's called harmonic oscillation. Harmonic. Yeah, the energy interchange to each other, and the average energy, they're all the same. The kinetic energy and potential energy. Okay, and also the final part is okay. Let's get the also get the relationship between the velocity and position. Velocity position. Yeah, we use the same analyze tool, energy conservation. Total energy equal to 1 over 2 mv squared plus 1 over 2 kx squared. And since we already know the total energy of the system is 1 over 2 Ka squared, okay? So we just do arrangement, we get the velocity is a function of the x, okay? Velocity of a function of x, okay? And then we will use this graph to explain this result, but okay? Because at the end position, okay, and at end position, because equilibrium position is here, so here is a, and here could be a minus a. At the amplitude position, the velocity is 0, right? Because you put x equal to a or x equal to minus a, this velocity will be 0, right? Velocity means velocity 0. That means you have the lowest kinetic energy, right? But energy is conserved. Lowest kinetic energy means at this position you have the highest potential energy. And equilibrium position x equal to 0, this is the maximum V. This is the maximum V. Okay, so at equilibrium position, you have maximum velocity. Maximum velocity means you have maximum kinetic energy. And that means because energy is conserved, maximum kinetic energy, that means you have lowest potential energy, which is 0. Okay, right? So actually, yeah, simple harmonic oscillation, they are pretty interesting. Okay, kinetic energy and potential energy are exchanging to each other. And also the average energy in one period also the same. And okay, and at the terminal point, velocity is velocity minimum, but potential energy is maximum. At the middle point, kinetic energy is maximum, but potential energy is minimum. Okay, so this is the energy perspective of simple harmonic oscillation. It's not very difficult, right? Okay, so and next we are going to show one example in textbook, and the other example just let you use energy approach to analyze the simple harmonic oscillation. Okay, and previously we used the result of equation of motion, right, to analyze simple harmonic, to do the example of simple harmonic oscillation. Yeah, position function, velocity function, acceleration function. But in the next example, we use energy perspective to solve a similar problem again. And you will see, yeah, using energy is much easier. Okay, like a previous example, energy conservation. Using energy is much easier to do. Using energy perspective is much easier to do the calculation. Okay, so see you in the next video. Okay, so we'll stop video here and see you in the next video. Bye bye. Yeah, bye 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 bye. Yeah, is this guy? No, this is guy. Okay, okay, see you. Bye bye. Yeah.